Hello, everybody. Up next is Understanding Python Debugging Internals with Liran Haimovitch. Thank you.
Hi, everyone. So my name is Liran, and I'll be talking today about Python debugging internals. How does it work behind the scenes, and what can we do about it? This is my first time at PyCon, as well as my first time is giving this talk. So I'd appreciate any feedback you have on it. So, sorry about that. So, start by introducing myself. My name is Liran Haimovitch, and I'm a co-founder and CTO at Rookout. Before founding Rookout, I spent about a decade doing cybersecurity. Now, in the cybersecurity space, much of what we do is reverse engineer software, trying to figure out how it works, how can we stretch it to the limit and beyond, and how can we change its behavior of what it was originally meant to do. So, Rookout is a platform for live data collection and delivery. It allows you to debug applications anywhere. And my background in cybersecurity and much of our employees helps us a great deal here. Rookout allows you to attach to a process running anywhere in the world, not only on your machine. It can run in the cloud, it can run in Kubernetes, it can run in serverless. And we allow you to set non-breaking breakpoints in those applications and get variable state, get stack traces, get anything you want from the application without writing more code, restarting the application, or redeploying it. Now, as I was writing the Rookout SDK for Python, I learned quite a lot about how Python debuggers work behind the scene and how does it actually function. So now I want to share with you some of what I've learned. So what's your favorite debugger? Actually, GDB does have support for Python debugging. Yeah, that's two different debuggers. You have GDB support for Python, and you have the PDB, which PDB is a debugger built into the Python standard library. I've heard outside, I didn't know it, that Python includes now two new debuggers. The breakpoint, which was released in one of the latest versions. And it's also, people have been talking a lot about IPDB, which I haven't heard about. You have the PyDev debugger, which might be the most popular one out there. Both PyCharm, which have a booth outside, and Eclipse use PyDev debugger behind the scenes. Rookout supports debugging Python as well as Node and JVM. Python Idle, Atom, each have their own built-in debuggers. And I'm sure there are others out there. What almost all of those debuggers have in common is that they are based on the sys.settrace function. This function, I'm not expecting you to read this documentation. Those are the official docs for sys.settrace in the Python manual. I think that's 2.7, but I'm not sure where I took the screenshot from. Anyway, this just might be the most complicated function in the Python standard library. And while the documentation for it has improved quite a lot since I got to know it 2 and some years ago, I'm going to walk you through it step by step. So, what does sys.settrace do? What does sys.settrace do? What is it all about? Well, with sys.settrace, you register a callback for the Python interpreter. And whenever the interpreter decides something important is about to happen, it's going to call your callback and notify you just before it does. What are those events? Function call, line execution, function return, and exception raised. Before any of those events, you're going to get a callback. Let's take a look at a quick example. Here we have a very simple tracer callback. It's called simple tracer, and it accepts 3 arguments. Frame, which provides you with a window into the interpreter state. Frame is what's the state of the interpreter just before the next event is about to happen. Let's say if the event is line execution, then frame is going to be what's going on just before the line was executed. Where in the code we are, what's the line number, what are the local variables, what's up the stack, and so on. Event is a string describing the event that we are just receiving. It's going to be either call, line, return, or exception. And arg is an additional argument that provides us a bit more information about the event. What does our simple tracer does? It starts by collecting information on the frame. It collects the function name and line number, and then it prints the event, function name, and line number to the standard output. Finally, our tracer returns itself, which we'll discuss a bit more later. Let's take a look what happens when we run this example callback against a sample Python code. This is our example. Method A returns B multiplied by 2. Function B returns response from B. And sys.settrace, simple tracer. We call settrace and set our tracer as the callback. And we invoke A. What's the standard output for that? Sys.settrace has no output. Neither does A. But once we invoke A, our callback is executed for the first time. We get a call event, which means a frame is about to be created, a function is about to be invoked. The function name is A, and the line number is 1. The next event is line. Line number 2 is about to be executed as part of function A. Now we get the third event. Function B is about to be called. Line number is 4. And line 5 is about to be executed as part of function B. Next, we are going to get a return event. We return from B with line number 5, and we return from A with line number 2. So that's a very simple flow of what happens with the tracer. We get every time a function is invoked, a line is executed, and the function is about to return, we get notified, as well as exceptions, which I've left out from these examples. Now, I've mentioned that simple tracer returns itself. If you were to look at the debugger implementation of all those debuggers we mentioned earlier, you would see that they often return the function at the end of its function. Not always, but sometimes. Why is that? Well, there are actually multiple callbacks working here behind the scenes. When you call sys.settrace, you register a global trace callback. This global trace belongs to the thread you are in and is going to be invoked anytime a new function is about to be executed. So whenever a function is about to be executed, whenever a new frame is about to be created, the interpreter will call our callback. Now, the return value for that callback is going to determine the local trace for that function. So, and the local trace will be the one receiving the local events. So line, return, and exception are only be received by the local trace. If the global trace will return none, then there is going to be no local trace for that function, and the local events won't be triggered at all. A few more things that are important to know, that the global trace is the one determining the local trace. Whenever you're in a function, regardless if there is a local trace or there isn't a local trace or what's the local trace, the global trace is the one that's going to be invoked in order to determine what's the local trace for it. And the last thing to keep in mind is that Python offers us no way to determine the local trace once a frame is started. So if there is a long-running function that has been invoked before you have called setTrace, there is no clean way to set the tracer for it. Now, let's go back to our example and see when are those traces are created. When we call sys.settrace, the global tracer is created and set a simple trace. When A is started, we return simple tracer, so it is set as the tracer for function A. And when we call B, that tracer will be set. The reason Python gives us this power is because the local tracing has a significant performance impact. So Python allows us to decide which functions we want to monitor and which ones we want to skip so that we can minimize the performance overhead for the debugging. Now, I'm curious. As I've mentioned, the setTrace sets the trace function for the current thread. How do you handle multithreading? Well, lucky for us, the threading module provides a setTrace function of its own. The threading setTrace functions allow us to pass a callback that will be registered as the global trace function for that thread, for any new thread created by the threading module. Essentially, after you call threading setTrace, whenever threading creates a new thread, it will call sys.settrace on your behalf with the value you have provided. Now, a couple of things to keep in mind here is that if you want to debug a multi-threading application, you want to call threading setTrace as early as possible. Once the thread is started, there is no easy way to set the global trace function for it. The second thing to keep in mind is that this is part of the threading module. If somebody is using the underlying thread module or a different approach to multi-threading, then that's not going to help you, and you need to figure out a different way to do it. On a happier note, if the application you are debugging is using an event loop-based concurrency model, such as gevent or eventlet, then for all Python kernels, there is only one thread. So as soon as you've called sys.settrace, you are set, and all the greenlets will share your global trace function. Now, this might be a bit intimidating, everything we've been talking about so far, and it might make you wonder how hard it is to build your own debugger. Well, there is a quick shortcut I'm going to teach you that allows you to build your own debugger in just 3 simple steps. Well, we've mentioned earlier Python PDB, the Python debugger. Well, PDB is built on the top of a lower level package inside the Python standard module, which is called BDB, the base debugger. The easiest way to build a Python debugger is to inherit from BDB and customize it to your own needs. So what does our debugger look like? A class debugger, which inherits from BDB, and does 3 simple things in its constructor. We call the underlying BDB constructor to initialize the class we inherited from. We create a dictionary for breakpoints we want to keep track of, and we call setTrace. What setTrace does is it actually has BDB registers its own trace function as the sys.settrace function. So BDB calls sys.settrace on your behalf, registers its built-in trace function. Next, we add our setBreakpoint function method. We accept the file name and line number we want to set the breakpoint on, and we get a method. This is the method we want to execute as a callback whenever the breakpoint is triggered. We call setBreak, which is a function we inherited from BDB, that have BDB sets the breakpoint in its own internal data structure, and we update our breakpoints dictionary with a list of methods to be called. So if there is no method, we go to the key error exception clause and add a list with a single element. If there is already a list, we just add our method to it. And last but not least, we override userLine. UserLine is a BDB method that says nothing but pass. But whenever BDB wants to inform us that the userLine is about to be executed, it calls userLine. So all we have to do is override it, and we get notified of any breakpoints and other significant events. The only argument for userLine is frame, which we've mentioned earlier. It provides the state of the interpreter just before our breakpoint is hit. What does our userLine do? It starts by checking if break here. BDB will occasionally notify you on events besides a breakpoint you have set. So if you want to make sure a breakpoint is actually on this line, you call break here, returns true or false, and in this case, if there is no breakpoint, we just return. We then get a file name and line number from the inspect module of the frame. I'm going to talk about inspect a bit later in this talk. And then we get from the breakpoints the callbacks that have been registered for this file name and line number, and we execute each of them with the frame object. That's it. In those 3 simple steps, we've built a breakpoint-oriented debugger for Python. Now, you may be wondering, how fast is it going to go? What's going to be the performance impact on my application using this debugger? Well, as I mentioned, Rookout is a general purpose data collector and debugger that aims to run in production. So we are obviously aiming for a very, very low overhead. So what we went, and after building that simple debugger, we went and tested it. Here is the simple performance benchmarks we've done. We've written 2 very simple methods, one that does nothing, and one that has 10 assignment statements. And we are going to execute each of those functions 16 million times. And then we're going to see how much time does it take in 4 different scenarios. The first, how long does it take without a debugger? How fast is Python in executing those functions so that we can have some baseline? Second, we are going to run it with a debugger, but no breakpoints. Third, we are going to run it with a debugger, setting the breakpoint in a different file. And fourth, we are going to run it with a debugger, setting the breakpoint in the same file. It's important to keep in mind that in all cases, the breakpoint is never going to get hit. We are never measuring the overhead of the breakpoint itself, but the global overhead of how slow are we making the software. So here are the initial results. If somebody can't read from far, that's very bad. Without a debugger, each function takes in average way under a millisecond. But once we turn up debugging, then performance is about 100x slower. Not very good for us. So how can we optimize this? There are 3 major avenues you need to consider when optimizing the debugger. First, as I've mentioned, local tracing is much more expensive than global tracing. You get notified on a lot more events. So as much as we can avoid local tracing, as smart as we can be about deciding where we want to local trace, and as we're not to local trace, the better we are at pruning out those functions we don't care about, the faster it's going to go. The second part is optimizing the call events. Whenever the global interpreter, the global trace function is called to determine whether or not we should trace a function, we need to make the decision as fast as possible. The faster we make it, the less overhead we have. And third but not least, once we've gone into local tracing, once we are looking at a specific function, we want to determine very fast if this line is a breakpoint or not. If it is, we need to stop. If it's not, we need to resume execution as fast as possible. So we went through the BDB source code, forked it to the side, removed a lot of unnecessary features, simplified the code, and optimized for hot branches. What were the results? That's much better, especially on the left side, where we managed to avoid local tracing. You can see the performance impact is still significant, but nowhere near where it was. But on the right side, while we still have local tracing, then the performance overhead is quite huge. How many of you are familiar with Cython? Oh, that's a lot. So Cython is a pretty cool project. It allows you to take your Python code out of the box and as is, transpile it into C, compile that C code, and place the generated shared object, or DLL, as an exact filler for the Python code you have dropped. So that Cython essentially allows you to create a much faster replacement of Python code with virtually no code changes. If you want, you can even do additional optimization based on Cython features that will push performance even faster. So we went around and did that. And as you can see, Cython gave us a pretty big performance boost, about 2.5 times faster, which is nice, significant. But seeing this graph, I was getting desperate. I mean, we are looking for a performance grade debugging solution, something that will have somewhere between no overhead to maybe, I don't know, 5%. And that's not 5%. So I took a minute to stop and think about what I was doing. So it's quite clear that Python BDB is very naive. It was never optimized for speed, and we can improve it by a lot. But the more we improve it, the harder it gets to keep improving it. The harder it gets to make it even faster. And we're pretty far from where we want to be right now. So what happens if we set an empty tracer? How fast is local tracing going to be if we do nothing? We get called, we return, no processing at all. It won't be much, it won't do much. It obviously won't provide us the functionality we need, but it's going to give us some benchmark about how fast can we make it. So this is what I ended up with. Even with an empty tracer, performance takes a big hit, especially once you turn on local tracing. Now, there are still saying this, I decided to take a step back and take another look at the CPython source code to understand what's going on behind the scenes. I'm not going to belabor you with everything I've learned. I'm just going to show you some of the top insights. So turning on tracing sets up CPython for extra work. Some of that extra work happens in Python, since for every instruction that's about to be executed, we'll be running additional Python code. And this is where most of our optimizations have been focused on. This is what we can change. Unfortunately, some of the performance penalty comes from the C code of the Python interpreter itself. For instance, here's a screenshot of maybe call line trace. I'm not expecting you to read it, but what maybe call line trace does once you turn on tracing is that after every instruction is executed before the next instruction, the interpreter has to go and figure out, is this a new line event? Is this something I want to notify you about? And this is just one of the many cases where CPython has to do a lot of extra work for the debugging mechanism, regardless of what you do on your end. Now, as optimizing this code is definitely possible, but it would require a pull request to the Python source code, and even worse, it would require new releases, and we obviously want to support customers without having them change the Python interpreter. We kind of gave up on the tracing mechanism. It's very awesome. Most Python debuggers out there use it, but it just wasn't good enough for us, not for what we had in mind. So to explain what we did, I'm going to take a step back. How many of you are familiar with the Python bytecode? That's tougher, yeah. So here is the Wikipedia definition for bytecode. It's a formal instruction set designed for efficient execution by software interpreter. Essentially, Python compiles our sources into its bytecode and executes that, rather than our own original source code. Let me give you an example. Here is a very simple method. Def multiply AB, result equals A times B, return results. Do any of you have any idea what's the bytecode of that going to look like? Oh, that's close. Yeah, that's exactly what he said. To be fair, that's exactly what he said, and even I can't read that. But bytecode is just a buffer. In Python 2, buffers are strings, so we get a nice string. It has a set of instruction set. It's much shorter than our string with the def multiply and stuff. But instead of going through syntactic lexing and syntax trees and so on, the Python interpreter stores that. I'm sure all of you know the PYC files. So that's the content of the PYC files. It's just the bytecode generated from your code. But once we disassemble this string, we get something that's quite more readable, which is quite close to what the gentleman said. Load into the stack A, load into the stack B, binary multiply the both of them, store it in a variable called result, load result back onto the stack, and return it. Now, if we take a look back at what the interpreter is actually doing, it looks a bit like this. There are two main stages. The first is compile. During the compile stage, the interpreter goes through our source code, figure out what it all means, and builds the bytecode, which is a string like which we've seen, stores it in PYC files or just in memory. And then comes the second step, the execution step. During the execution step, the so-called interpreter loop is literally looping through our bytecode and doing it one step at a time. Now, there was actually a lecture about an hour ago about the GIL, which is the dreaded GIL everybody's been speaking of. That's the interpreter loop. The GIL is about the interpreter being able to execute one set of bytecode at a time. It can't run multiple threads of the interpreter loop. And everything we've seen so far about the sys.settrace and the tracing mechanism, it all takes place during the interpreter loop. So whenever the interpreter does something that we might care about as a debugger, call a new function, execute a new line, return from a function, and so on, the interpreter has to notify us. And that's what the performance overhead we've seen happens. Every time the interpreter does something, it has to notify us. And that's expensive. So Rookout is taking a different approach. Rookout goes back to the bytecode that we've seen. It finds the line of code that belongs. We find the instruction, the specific instruction that maps to the line of code using the debug information, and we insert our breakpoint. We literally just insert a call instruction into the bytecode, so the interpreter doesn't really care about Rookout. The interpreter just goes through the code happily, not aware of tracing or any debugging mechanism, but when it sees that call instruction, which is the same as any other call instruction it might have, it calls it. And that's when Rookout gets notified, and this is where we differ from all the other debuggers out there. We don't work with the interpreter step by step, tracing everything it does. We try to avoid the interpreter being aware of us at all, just being there when it needs to be. While bytecode manipulation is a big topic and might deserve its own lecture, I do want to give you some resources about where you can read more about it. So the Python standard library is two important packages that can definitely help you with bytecode manipulation. The first is inspect. Inspect is a package that allows you to see into the interpreter, take a look and see what the interpreter is doing. Among its other useful functionality, inspect allows you to extract the bytecode for any function or class you have in memory, and it was used when I showed you. For me showing you the bytecode, I used inspect. The second package is this. This is short for disassemble, and it allows you to take those ugly strings we've seen and make them into something a bit more human readable. Now, unfortunately, Python does not offer any way to write bytecode in memory. So you can read it, but you can't write it, you can't edit it, you can't change it. In order to do that, you need a native extension that bypasses the Python standard interfaces and interacts with the CAPIs. If you're interested in that, Google has an open source project called Cloud Debug Python that does a bit of it, and you can take a look at that. Now, so far we've discussing how do you know when to break? How do you decide which line you care about? When do you stop the application and take a look? But what happens after you break? How do you take a look at a running application and understand what's its state, what it's doing? So if you remember, the frame, as I've mentioned throughout the talk, is our window into the interpreter. It allows us to see exactly what is going on. Additionally, the inspect built-in module is quite well documented. It's easy to use. It allows you to see the line numbers, file names, stack traces, and so on. And unlike what I've shown you earlier in this talk, everything here is very, very fast. Performance is awesome due to the simple fact that everything we're doing here through the inspect module is quite similar to what the interpreter is doing behind the scene. So when the interpreter is working with your code, is running your code, it's using the same data structures and the same utility functions we are discussing here. So here is a simple example. Function test frame info. Frame equals inspect current frame. Now, inspect current frame is one of the coolest functions out there. It allows you to literally get the frame of the code you are currently executing. This has some production uses, which we might cover a bit later, but it's also the most useful function you can have if you are testing or experimenting with the bytecode and the Python interpreter. As you get on the fly, you can just get the frame, and then you can see what it's doing, and even run. Most of our unit tests are built using that function. So this is the output for it. You get the file name, frameinspect.py, which I'll show you the repo for a bit later. Line number 16, function name, code context, index show where we are up in the stack trace. Since as we are currently executing, the index is 0. But we can also traverse the stack trace and go up. And the second example, let's take a look at how do we access local variables. My str is a string, my dict a dictionary, my list is a list, and here we print flocals, part of the current frame. Does anybody have any idea what's that going to do? So turns out that behind the scenes, the local variables are stored in a dictionary, just a regular Python dictionary, and that's flocals. So once we print it, we get a dictionary. Variable names are keys. Variable values are the values of the dictionary. So my dictionary, my str string, and my list. Quite easy, unlike what I've shown you earlier. So what can you do with what I've been showing you so far? First of all, you can show off your Python skills. That's definitely useful if you're here at PyCon. You can get source information. Have you ever wondered how does the logging module know the file name and line number you are writing the log from? So the logging module uses inspect current frame and walks up the stack to find who called it. And from that frame, gets the file name, function name, line number, and that's how you get that information in your logs. You can also walk up the stack if you're looking at profiling, or you just want to get that extra variable somebody forgot to give you in the interface. You can always go up and get it. Or you can build your own debugger. So I've placed most of the source code that this lecture is based on at our public repo. So feel free to go ahead and browse it. And that's kind of about it. Feel free to check us out at rookout.com and ask me more. And yeah, so now it would be a good time for questions if you have any on what I've shown you.
Great presentation. Thank you.
Thanks.
I wonder about the bytecode manipulation. Can you manipulate the bytecode which has been loaded into memory?
Yes.
Okay, and if you do that, what do you need to, there are any security which you have to pass to do that? Or, how does this work?
So Python doesn't have any built-in security module. Everything running in the application is at the same level of isolation and security and trust. So all you have to do is use the native C APIs that are not exposed to Python, and you can use them to edit.
So you said you can do remote debugging, so I don't have to do anything on the remote machine to be able to modify that bytecode?
Yeah, so that's, to do bytecode manipulation, you need to be in the same process. What Rookout does is that you install an SDK. You install an SDK that connects back to our service, and then only you can access that machine remotely and debug it.
Sorry, hang on. The microphone in the back got mobbed, so. Oh, yeah. Go ahead.
Hi. When would you use when would you use flocals instead of just the locals function?
I knew that once. I can't remember right now, but they're essentially the same. The locals function returns you that dictionary.
Okay, that's all I needed.
Hey, it was a great presentation. I was wondering if you had any performance numbers with the bytecode way of doing, how it.
Yeah, I have some. I can show you.
Yeah, I was just wondering how much faster it is compared to what we were looking
So
at earlier.
the global override is nothing because the interpreter doesn't see anything or doesn't care anything. Even the breakpoint itself takes under a millisecond to execute. So I have some performance metrics if you want to see on my laptop.
All right, thank you.
When you manipulate the bytecode there, are you doing a insert in place and then a jump table somewhere for the extra bytes, or are you just actually extending the whole thing
So you
it's
have to
longer?
expand. You have to, at least at the function level, you have to expand. But you have to keep in mind that unlike more traditional languages such as C, the Python doesn't build just one big buffer of code.
Yeah,
It
it's
builds
got
a
a
lot of
bunch of little
small
code blocks.
buffers.
Yeah.
So you
Okay.
just have to expand the specific buffer you are editing. And over there, you have to expand it because there are pointers for jump instructions and loops and debug information and so on.
Okay, so the cost penalty for actually doing all like the mem copy and that, you don't worry about it, it's low?
It's copying a few bytes in memory.
Yeah, okay.
That's nanoseconds.
Hey, if you are in a debugging session, then your code calls sub-process call. And I cannot really go into the process that I call in to continue to debug. I just wonder if you have any tip.
Again, so most of this talk has been about Python debugging in general. For Rookout, you install the SDK into your application.
Okay.
And once you install the application, then you can debug that process because it creates a network connection.
Okay.
I can show you later, but
Hi, thank you very much for your talk. Just out of curiosity, have you ever tried to use your knowledge to kind of set a bunch of checkpoints in a malicious code that you know is malicious? And is it even safe to do it? Probably not. I don't know.
so
'Cause
we
yours-
actually had that talk with a few security professionals about setting breakpoints in a malicious code they want to debug. I haven't seen much rise from it yet, but it doesn't make any difference from a technological standpoint. Just like you debug a piece of code you don't know, it doesn't matter if it's malicious or not. It's not very different from running a malicious piece of code with WinBug or GDB or whatever. You can do it.
So that's safe, right? I can use it to, let's say I have a piece of malware, and I can use your approach to analyze bytecode of this malware.
Yeah, if you have malware written in Java, Node, or Python, you can definitely use Rookout, debug it,
Thanks.
which would definitely help regards if they have anti-debugging tools and so on, they're probably not going to detect it.
I had a lot of trouble using performance issues using the inspect library. I found when I was trying to build something similar, it was slowing things down a lot compared to using the sys library to get the frame. I ended up giving up on it. Is there a reason do you have to use the inspect library as opposed to other ways of getting a current frame?
It's all the same. As long as you get the current frame, that's good. Inspect does offer a bit of overhead, and we generally try to use it a bit less when we're actually running production code, but I'm not sure.
Thank you, everyone.